Hi, I'm James Bishop, and today I'll answer what is machine learning. Then I'll give some examples of applying machine learning to DoD problems. Then I'll discuss classic methods of addressing the same problems. I'll discuss how machine learning complements our attempts to estimate causal relationships. And I'll finish by outlining what has enabled new applications of machine learning over the past decade or so. So what is machine learning? All we need are a few definitions. Let's define a model as a mapping from an observation to an output. The output for a given observation depends on model parameters. Let's define learning as the use of data to set model parameters. When a machine uses data to set model parameters, we call it machine learning. We're done. We define machine learning. Okay, I admit there's more to unpack here. Let's establish some concepts. We start with some incomplete information on a single thing. That information comes from the universe of complete information on everything of the same type. We want to use our information in some way. Perhaps we want to summarize or otherwise characterize it. Perhaps we want to infer some related information. Perhaps we want to decide on a course of action. To transform our information to whatever we want, we need a model. We have various innumerable options for the model we choose. But even given our choice of model, our output will depend on the values of those models' parameters. We can use information on other things of the same type to choose those parameters. This process is called learning. If a machine is doing it, it's called machine learning. If we want to characterize our information, everything we need is all here. However, if we want to infer related information, we need that related information in our data. And if we want to decide a course of action, we need to know those courses of action and the resultant rewards. There are DoD applications for each of these kinds of outputs. For example, acquisition programs generate thousands of pages of information, only a few of which may be relevant to a given topic. Given the text of a single document, section, or sentence, we may want to characterize that text with a topic label or condensed summary. We typically want to maximize the information we keep, but also maximize conciseness. Methods to address this problem are the domain of unsupervised learning. As another example, personnel data allow us to infer when service members are likely to separate. We want members' future separation behavior to be matched by our inferences as closely as possible. More generally, we typically want to maximize the similarity of our inferences to the ground truth. Methods to address this problem are the domain of supervised learning. For one more example, autonomous drones use sensors to inform their actions. We want drones to maximize the probability of mission success by choosing the optimal actions. Methods to address this problem are the domain of reinforcement learning. We see that DoD has problems relevant to each domain and that all three involve optimization. We define machine learning as a machine using data to set the parameters of a model. What are the alternatives? For one, we could have humans set the parameters of a machine-operated model. In the context of text labeling, this could mean a human specifying a search string and a machine finding instances of it. In the context of retention prediction, this could mean a human choosing how to group personnel, then a machine computing the historical retention rates within each group. In the context of autonomous drone training, this could mean a human programming a set of rules for the drone to follow in the field. These alternatives have many advantages. They're reliable, they're cheap, scalable, and transparent, but they have critical disadvantages. They're not at all versatile. They can do only one job, and they will never be superb at it. We could also have the model itself be human rather than machine. In the context of text labeling, this could mean an assistant sifting through those thousands of pages to find the most relevant snippets. In the context of retention prediction, this could mean a human reviewing personnel records and eliciting information from other humans to infer who's about to leave. In the context of drones, this could mean a remote human pilot. Humans address the critical disadvantages of classical automated systems. They're supremely versatile and become wizards at their jobs. However, they're unreliable. A machine will never get tired or disgruntled or procrastinate. They're expensive. The most powerful EC2 instance on Amazon Web Services for training ML models costs at most $32.77 per hour, less than the typical researcher. They're not scalable. No human can review the personnel records of everyone in DoD. And if you think machine learning models can be black boxes, humans are pathetic at explaining their own thought process, even in the exceptional case where they're being entirely truthful. Machine learning hasn't gotten us all of these advantages, but it has pushed machines beyond human performance in a variety of domains, including dogfighting. For now, machines with human-level versatility remain confined to science fiction. One activity that will require humans for the foreseeable future is causal estimation. If we want to know how changing one piece of our data, X, say, will cause another piece to change, we'll call that piece Y, we need to consider all the remaining parts we don't observe. Because if changing something we don't observe would change X and Y, we won't be able to distinguish those causes from the causal effect we are trying to estimate, the effect of X on Y. To argue that we can estimate a causal effect, we need to posit an assumption. We could posit that our model emulates the underlying causal structure that produces variation in Y. This strategy is called structural modeling. Another strategy is to posit that either nothing unobservable affects Y through X, or nothing unobservable affects Y except through X. This strategy is called quasi-experimental design. Note that these arguments do not prescribe how to set the parameters of a given model, whether by machine learning or some other method. If our data don't support an identifying assumption like these, we need to make data that do by performing an experiment. Causal estimates can inform us about the impact of an action in a given instance, but they aren't helpful until we identify the instances where the impact is worthwhile. For example, we want to identify the most important documents before deciding how much time to spend on them. We want to avoid wasting retention resources on members who we're going to keep serving anyway. And our capability to blow something up isn't useful if we don't know whether or not we should. So why are we using machine learning now? There's no single reason, but a confluence of technological advancements. Advancements to hardware, GPUs, TPUs, more RAM in commodity hardware, and cloud access to enterprise hardware. Software, packages like Pandas, Tidyverse, XGBoost, Keras, and Torch, just to name a few. Apache Spark for cluster computing. Data, more features, longer panels, and easy access through APIs. And community, Kaggle for validated methods, GitHub for source code, Stack Exchange for support, and Archive for manuscripts. As these advancements continue, we can expect greater use and usefulness of machine learning. Thank you for your time.